Okay, hello everyone. I'm Alan. Welcome to exercise class 3. So in this exercise class, we are going to cover 3 types of questions, including tensors, some metric or physics in curved space-time, and also one question about special relativity. So before you start, before you continue to listen to this lecture, please go through some time to try to answer the questions yourself. So if you haven't do any of these questions, please pause the video right now. Okay, so I assume everyone have at least tried the questions. So let's start the exercise class now. Okay, so for the first questions about tensor, you are asked to prove the following 3 tensor identities. So this question is basically talking about some symmetric and or asymmetric tensor to test your understanding of symmetric and asymmetric tensor. So a quick recap. If you remember during the lecture, we have already introduced what is an antisymmetric tensor. So for antisymmetric tensor, basically, for example, for A alpha beta, if you swap the index alpha beta, then there will be an extra minus signs in front. So if you swap 2 indices, then you have a minus sign. On the other hand, for symmetric tensor, let's say for this time B alpha beta, if you swap the index, the tensor will remain unchanged. It is still same as the tensor before you swap the tensor, before you swap the index. Okay, so that's the property of symmetric and antisymmetric tensor. So with this knowledge, you can already, you have the ability to finish the question ABC. So let's start. Question A. So in this question, we are contracting to rank 2 tensor, A and B, where A is an antisymmetric tensor and B is a symmetric tensor. So, and you're asked to prove that for whatever antisymmetric tensor and a symmetric tensor, if you contract these 2 tensors together, the result will always be 0. So how to prove that? So first of all, since B is a symmetric tensor, if you swap the index, everything remains unchanged. And on the other hand, since alpha and beta are dummy indices, they appear twice in the equations, so they're just representing summing up all the indices. So it doesn't matter whether you use alpha or ijk for representing the dummy indices, because dummy indices basically represent summations. So for the next line, I change alpha to beta and beta to alpha. Okay. So what we have is A beta alpha and B alpha beta. So basically, you're just interchanging 2 indices, or actually it's renaming the 2 indices. So I put beta in alpha and alpha in beta. Okay, so for the second properties, for A, since it is an antisymmetric tensor, again, if we swap the indices, from beta alpha to alpha beta, then we have an extra minus sign in front. Okay, so up to now, we obtained a form exactly identical to the left-hand side with an extra minus sign. So a scalar equals to the negative, the minus of itself. So this scalar must be 0. Oops. So therefore, A alpha beta, B alpha beta equals to 0. Okay. So for part B, the way to do it is quite similar to part A. Once you know how to do it. So in these questions, A again is an antisymmetric tensor, and C is an arbitrary tensor. So, okay, let's start. So basically, first of all, we use the antisymmetric properties of A. We swap the index alpha beta to beta alpha with an extra minus sign in front. And then again, we rename the indices. So we put beta into alpha and alpha into beta, because alpha beta are basically dummy indices. They are not free index. So what we have is A alpha beta and C beta alpha. Okay, so this time, since C is an arbitrary tensor, you can not use any properties of asymmetric or antisymmetric tensor. So how we obtain the form in the questions. So basically, we are adding both sides this term. So for the left-hand side, we have 2 A alpha beta, C alpha beta. And for the right-hand side, we have the one we obtained, we derived before, plus A alpha beta, C alpha beta. And since, well, we have A alpha beta here, you can actually group them. To be this form. Okay, so therefore, we divide the whole equation by 2, then we can prove it. And notice that this form, C alpha beta minus C beta alpha over 2, can be actually written as C blanket, actually parenthesis alpha beta, C parenthesis alpha beta, where this notation, the parenthesis, basically mean 1/2 alpha beta minus beta alpha. You permute the 2 indices and then add an extra, oh, sorry for this one. It should be a square bracket. Okay, I better use another color pen. Okay, sorry. C square blanket alpha beta. So basically, it's like the commutator you have learned in QM. So for square blanket is the commutator. So it's like basically permuting the index with a minus sign and also over 2. So this square blanket is actually anti-symmetrization of the tensor C. So what it is basically is extracting the anti-symmetric part of C, of this rank 2 tensor. Okay, so, and for part C, the way to do this is basically the same So I just quickly write this down. So first of all, B is a symmetric tensor. So you swap the index of B alpha beta to beta alpha with nothing changed. And then again, you rename the index. You rename alpha to be beta and beta to be alpha, since they are dummy indices. So right now you obtained B alpha beta and D alpha beta, beta alpha. And again, you're adding both sides with the terms in the left-hand side. And then you can group B alpha beta in the right-hand side. And what you have left is D beta alpha plus D alpha beta. So therefore, you divide both sides with by 2. And then you can you finish the proof. Again, for this term, D alpha beta plus D beta alpha over by 2. Over 2, this term, you can write it as D, this time parenthesis, so a round bracket alpha beta. So there is a parenthesis including the index. So what does that mean is that, again, you permute these two indices, but this time with a plus. You're adding them all up instead of adding a minus sign there. So this parenthesis is the symmetrization of a tensor. So what you basically did is extracting the symmetric part of this tensor. So note that for any rank 2 tensor, for any rank 2 tensor, let's say Tij, it doesn't matter where they're covariant or contravariant, whether they're upper indices or lower indices. As long as they are rank 2 tensor, you can always split the rank 2 tensor into 2 parts. Okay. For the parenthesis part, this part is the symmetric part of the rank 2 tensor. And for this part is the anti-symmetric part of the tensor. So for any rank 2 tensor, you can clearly divide out the symmetric part and the anti-symmetric part of the tensor. Okay, so that's all for part question A. Okay, for question B. So for this question, it's basically testing you some basic concept of metric. Okay, so in this question, you're given a line element ds square equal to, well, for the latter part, it's basically the line element of the spherical coordinate. Just one difference is that for the GRR, it's not 1. It's 1 minus KR square, dr square. So in this line element, we are considering K smaller than 1 over root K. Sorry, for we are considering R smaller than 1 over root K. Okay, so let me move them closer together. Oh, crap. Okay. So in part A, you're asked to write down the metric tensor Gij from this line element. Well, this is easy because line element is basically equal to Gij times dxi dxj. So clearly from this line element, there is no dr d theta or d theta d phi. There's no cross term. So there's for Gij, there is no off diagonal term. So for any off diagonal term, there's 0. Okay. For the GRR, well, basically it's just the term in front of the dr square, 1 over kr square. And g theta theta is r square, and g phi phi is r square sine square theta. Okay, that's it. Easy. Okay, for part B, things gets a little bit complicated because you are asked to find the radial distance. So in this metric, you're asked to find the radial distance between r equals to 1 over 2 roots k and 1 over roots 2k. Well, since it's asking the radial distance, so it means that we don't have to consider the change in theta or phi direction. So that means d phi and d theta are both 0. So the line element will be very simple, just root GRR dr, which is 1 over root 1 minus kr square dr. Okay, so for the radial distance in this metric, you just have to integrate over the line element. So, well, it's basically integrating the whole thing, 1 over square root 1 minus kr square dr from 1 over 2 roots k to 1 over roots 2k. And you can, well, by some substitution, let's say u equal to kr, you can extract 1 over r outside. So then for the integration, we just have some dimensionless parameter inside the integration. So when you do this substitution, u equals to root k times r, what you have to do is just evaluate this integration. And I think this integration is not, well, it should be familiar to you guys, because the result is just r sine u with lower bound 1 over 2 and upper bound 1 over root 2. So the answer is pi over 12 root k. Okay, so that's the radial distance. And for part C, you have to find the volume included, basically the volume of the spherical shell, with radius, the lower bound and the upper bound of the radius same as the part B. So in this question, you just have to know what is the volume element in this metric. So by definition, the volume element of some particular metric is just basically the determinant of the metric tensor Gij times, well, times all the di, all the dxi. So in our case, we have dr, d theta, d phi. And the determinant of the metric tensor is not difficult to find in this question because we don't have any off diagonal terms. So the determinant is basically the multiple of all the diagonal terms. So, well, after taking the square root, we have the r square sine theta, which is the common volume element in spherical coordinate, or in flat spherical coordinate, with an extra term over 1 minus kr square, which comes from the grr term. Of course, dr, d theta, and d phi. So what you have to do is just perform this integration, integrating the whole thing, r square sine theta over 1 minus kr square dr d theta d phi, with the boundary of r is 1 over 2 roots k to 1 over roots 2k, and the boundary for theta is 0 to phi, and the boundary for phi is 0 to 2 pi. Okay, so, well, the integration for theta and phi is easy, just 4 pi in front, and you can do the similar substitution as part B, so that u equals to roots k r. So we have 4 pi over k to the power of 3 over 2 here. With this integration left, 1 over root 2 here, u square over 1 minus u square du. Again, by some further substitution, I think you all can handle this, or even you are too lazy to do the integration. I suppose there are a lot of resources in the internet for you to use or to do the calculation. So here I just write down the result. If you integrate the whole thing, you got something like this: 1 over 2 times outside u minus u times root 1 minus u square with this boundary. And when you substitute the whole thing back in, you get this thing. Okay, so that's the volume included. And well, the reason I asked you to do such calculation in this metric tensor is because later on, if we learn cosmology in this course, you will learn something called Friedmann-Robertson-Walker metric. Okay, so Friedmann, I just write the name here. You don't have to know what's going on. Well, that's the part of the metric inside the Friedmann-Robertson-Walker metric. So the metric we are dealing with here is basically a closed 3D metric form, which is used in the FRW metric, the Riemann-Robertson-Walker metric. Okay, so I just mentioned the name here. If you're interested, you can search it up. But Just a quick introduction. Okay. For question C, okay, let's go to question C. Spectral relativity. So imagine that the train is moving at the speed of 4c/5 passengers points a laser out the train window perpendicular to the tracks. And the laser emits a brief flash of light. What angle does the velocity of this light flash make with the tracks in the ground frame? Okay, so first of all, let O be the ground frame and O prime be the train frame. And this train frame is moving at V equals to 4c/5 for, let's say, in the x direction, because this problem is a 2D problem. So let's say the train is moving in the x direction, plus x direction. So right now we have beta equal to V/c, which is 4/5. Gamma equals to 1/√1 minus beta square, which is 5/c, 5/3. Okay, so with beta and gamma, we can write down the transformation matrix. The transformation matrix from the O frame to the O prime frame. So let's say this one is big gamma mu prime nu. So with this particular velocity. Okay, so well, a matrix form, well, I think all you guys should already remember this, the Lorentz transformation, gamma minus gamma beta and gamma here, and 1 in the diagonal terms of y and z, and for other parts 0. And after you substitute all the number in, it will be like you obtain this. The whole matrix will be like this. Okay, so that's the transformation matrix from O to O prime. So how about the reverse transformation? So what's the transformation matrix from O prime to O? Well, easy. Oh, so let's say the notation is big gamma. This time mu here, nu prime here. Okay. Well, one way to do it is that you can, well, because it's basically the inverse of the previous of the above transformation matrix. So you can do the inverse, or you can see another way is that if the train is moving in plus x direction relative to the ground, then in the train frame, the ground is moving in the minus x direction relative to the train. So basically, it's the same Lorentz transformation, but this time you're substituting minus v inside the matrix. So in matrix form, but since you are substituting minus v here, so there will be an extra minus sign in beta. So now we have gamma, gamma beta, gamma, and for the other 1 and zeros. So now you have the matrix quite similar to the previous one, just differ from some minus sign. So if you try to multiply these two matrices together, you obtain the identity matrix, the one. Okay. So for the train, assume the laser emits the light flash in plus y direction, because in the question they said the passenger emit the light in the direction perpendicular to the direction of the train. So let's say he emits the light in plus y direction. Right at origin, so at 0, 0, 0, well, 1, 0, 0, 0, 0 in the O prime frame, because it's perpendicular in the O prime frame, because in the the passenger is on the train, right? So x plus y direction in O prime frame. So the world line of the light flash would be, so let's say the path of the light, let's say is d prime, the prime because it's in the O prime frame. The d prime should be equals to c delta t 0 delta y and 0. Well, better add the prime here because it's in the O prime frame. So, well, since the light is moving in the speed of light, so delta y prime over delta t prime equals to c. So we have this as the path of the light in O prime frame. So now we have the vector. We know the transformation from O prime frame to O frame. We can find the world line or the path of the light in O frame. So this one is in O prime frame. And right now we are doing the world line in O frame. So the vector in O frame, d mu, is equals to the Lorentz transformation of d in O prime frame. So, well, we just have to copy this matrix. Oops. This transformation matrix here. Okay. Let me move it here. And the d prime is c delta t prime, 0, c delta d prime, and 0. So it is equal to 5 over c, 5 over 3 c delta t, 4 over 3 c delta t, c delta t, prime, and 0. So in the O frame, if there is an observer on the ground, then he will see the light not going in plus y direction, but with the angle with plus y. So basically, it's going to going at some angle with plus y direction. So this should be the new vector. And notice that if you check the space-time interval of D. Well, since D is describing the path of light, the space-time interval of D should be 0, right? So let's check it. Minus this guy square plus 4/3 theta D prime square plus this guy square. So after some calculation, you will find that, well, it's still 0. Of course, because we are performing the Lorentz transformation. The space-time interval is an invariant under Lorentz transformation. So they are both light-like or null geodesic or null world line for both frame. Therefore, the angle, well, we have to find the angle with the check, i.e. the angle with x-axis is basically arc cosine of delta x over delta x squared plus delta y squared. And from the results above, delta x squared, this is delta x, this is delta y. So we have arc cosine 4/3 c delta t prime over, well, we can just cancel the c delta t because we know that they are all cancelled out. C 4/3 square plus 1 square. So the final result is arc cosine 4/5. So that's the angle. So the light beam observed in the O frame is not perpendicular to the train. Well, it's not moving in the direction perpendicular to the train, but with some angle. Okay, so that is the answer for question C. So I will upload this solution to Blackboard right after I upload this video. So if you have any questions, any further questions after watching this exercise class, feel free to email me. Well, better use I think we have the help email for specifically for this course. So please use that email list instead of email me privately, because if you guys want to ask any questions, you better CC all TAs and also Professor Johnny. So it'll be much more convenient if you use the email list of this course, the help email. I think Johnny has already mentioned it during the lecture, or he should be uploaded, or he should have shown the email somewhere in the announcement. So that's the end of exercise class 3. So thank you very much for attending this class. So see you next time. Bye.